Education is the most powerful weapon which you can use to change the world. Believing in this principle, welcome to Murray Lakshman Reddy Group of Institutions, providing world-class education and research facilities to help transform people's lives for the better. It is the brainchild of a visionary who conceived and promoted it in 2005. Meet the man, Shri Murray Lakshman Reddy, who ushered in the silent mission. A mission to provide technological advancement from time to time, with the aim of imparting education with global standards to enrich values with knowledge in students. Succeeding the paths of Shri Murray Lakshman Reddy, making education a positive experience. Shri Murray Rajashekhara Reddy, Founder Secretary, nurtured MLR Group of Institutions to win the pride of being recognized as one among top engineering colleges in Telangana for the past consecutive academic years. Situated in vast and peaceful area of 35 acres, students here tend to learn experimenting their live projects through centers of excellence, which is tied up with various industries. Spacious and comfortable classrooms, corridors, advanced laboratories, with equipped ultra-modern audio-visual technology auditorium, accommodating 1,000 plus audience, separate hostels for boys and girls. Each student is specially taken care for the provision of health facilities and hygienic food in spacious and eco-friendly canteen, etc. are salient features of MLR Group of Institutions. AICTE recognized MLR Group of Institutions accredited by NAC with A grade and has NBA accreditation for all programs. MLR Sports Complex and inaugurated by MLR Group of Institutions with most advanced multi-sports facilities like cricket stadium, badminton court, table tennis, billiards and basketball, etc. MLR Sports Complex organizes many national and international university-level sports fests by grooming every aspirant in competing national and international sports forums. Successfully achieved 50 gold medals, 13 silver medals and 16 bronze medals at various national and international sports events. MLR Group providing free admissions every year by supporting aspirant under sports quota with scholarships for the meritorious sports persons to pursue their career in sports and opportunities in government sectors. To sharpen and extricate students' creativity and entrepreneurial skills, MLR Group has established Center for Innovation and Entrepreneurship with facilities like Social Square, Innovation Hub and Makerspace. The Makerspace is a technical prototyping platform for students' innovation and invention, which is loaded with ultra-modern equipments such as multimedia workstations, 3D printers, CNC machines, laser cutters, and thus provides stimulus for student entrepreneurs. The center has collaboration with various government and non-government ministries for raising seed fund to incubate student projects and startups. This center has developed 8+ market-ready products and supported 11+ student startups. MLR Group has set up livelihood business incubation in association with Ministry of Micro, Small and Medium Enterprise (MSME) to promote new technology or livelihood-based enterprises. Research and Development Cell has 12 centers of excellence in association with various industries and supports faculty and student research. It also has a track record of 25+ funded projects, 700+ SCI or Scopus journal articles, and 35 plus intellectual property rights, and the progress continues. In preparing the aspirants to the real-world competitiveness, MLR Group of Institutions has introduced Indo-Universe Collaboration for Engineering Education IUCEE to introduce outcome-based student-centric education and Bloom's taxonomy-based teaching, learning and evaluation process, engineering projects in community services EPICS in association with Purdue University USA. Scope: School of Programming Practices to hone the coding and programming skills. Students' Platform for Engineering Education Development SPEED empowers the students to become a factor of change in engineering education and its effect on society and environment. Club Literary to organize MUN, TEDx Talks and Techno-Cultural Fest to uplift student communication and English skills to the global forum. MLR Library is fully loaded with diversified study material, books, national and international journals with dedicated digital library along online subscription to massive open online courses, IEEE, Elsevier, Springer, ACM journals, etc. MLR assures the safety and security of the students. Its transport infrastructure includes modern and secure vehicles and strictly complied with RTA regulations with well-maintained safety standards. MLR Group of Institutions having faculty of nationwide experienced and renowned adjunct professors include the expert scientists of DRDO, DRDL, HAL, BHEL, SAE India, ECIL and JNTU, imparts education with pure practical inputs. Offers courses in BTech, Aeronautical Engineering, Computer Science Engineering, Civil Engineering, Electronics and Communication Engineering, Electrical and Electronics Engineering, Information Technology, Mechanical Engineering, MTech with Aerospace Engineering, Computer Science Engineering, Embedded Systems, Digital Systems and Computer Electronics, CAD or CAM Engineering, Thermal Engineering, MBA courses. MLR proudly announces that till now 75% of their students have grabbed the opportunities with average salary package of 6 lakh by holding premier positions in top-notch companies in global market. MLR relies always on the philosophy that intelligence plus character. This is the goal of education.
So, good morning, everyone. A warm welcome to the third day of the Faculty Development Program on recent developments in nanocomposites and smart materials in the aerospace industry. So, today's session, we are having the guest from NIT Raipur, Dr. N.V. Swamy sir. I take the privilege of inviting Swamy sir on behalf of Aeronautical Department as well as the management of MLR Institute of Technology. So, welcome to the session, sir. So, Swamy sir is currently working as Associate Professor, Department of Mechanical Engineering, NIT Raipur. He he's received his undergraduate degree in mechanical engineering from Andhra University, Vishakhapatnam in 1994 and a postgraduate degree in machine design from Andhra University in 1998. He completed his PhD in aerospace engineering from Indian Institute of Technology, Kharagpur. He has over 7 years of industrial experience in the field of aerostructures, design and analysis, and 16 plus years of teaching and research experience. He has 2 years overseas experience as a structural analyst for Boeing 787 Dreamliner at Seattle, USA, and Gulfstream Aircrafts, USA. He has executed various projects on various aircrafts like Airbus, Boeing, Gulfstream, etc. His research interests span both experimental and computational methods using FEM. His areas of interest are biomechanics, nanocomposite structures, functionally graded materials, solid mechanics with FEA, etc. Much of his work has been on improving the properties of composite materials, design and performance of laminated composite structures, mainly through FEA, and performance evaluation. He has examined the improvement of the solutions through finite elements. Also, he has made numerous contributions to the development to develop VBA macros in Excel for automation of FEA. He is presently guiding 6 PhD scholars and 1 MTech student. He published 40 plus technical papers in national and international journals and conferences and 1 book chapter. He has delivered numerous expert talks at various faculty development programs and workshops. He is a life member of professional bodies like Indian Society of Technical Education ISTE and Indian Science Congress Association, Aeronautical Society of India, etc. With this brief, I would like to take the privilege of welcoming Swamy Naidu sir to the session. So welcome sir.
Yeah, thank you, ma'am. Thank you, ma'am. Good morning to everyone, one and all. So, first of all, I would like to express my sincere thanks to this institute, MLRIT Institute. They inviting me again in this uh, program, that is especially in nano composites for aerospace applications. My sincere thanks to the Sweta ma'am and Gupta sir for inviting me, for giving me the opportunity once again to interact, I think, the different parts of the participants. So, thank you. And I also extend my thanks to the management, the MLRIT management in this regard. And I would like to start my presentation in this nano composite materials. First, I would like to give some brief about that nano composite materials, how widely they are using in the aerospace applications, that I want to cover within another 1.5 hours. Shall I start, madam? Shall I share the screen?
So please start sharing the screen sir.
Yes, yes. I think everybody can able to see my slides.
Yes sir.
Yeah. So audio is clear, no?
Yes sir, audio is clear.
Okay. All right. So nanocomposite materials for aerospace applications. So in this, I would like to cover the following items. So first of all, I will give the small introduction about that composite materials and advanced composite materials, and then move to the nanocomposites. Then I will give to the classifications of the nanocomposites, and in this different classifications are there. Maybe I will stress upon the polymer nanocomposites and aerospace applications and possibilities for the future also. So this is a research purpose, as well as somebody is interested to continue in these nanocomposites, they can still see that some of the challenging problems. So before going to start the nanocomposites, the introduction about the nanocomposites, actually the aerospace industry, what does the aerospace industry is required? What does the aerospace industry want? So mainly the aerospace industry, they will see that the lighter weight of the stronger material and more durable and resistance to the extreme conditions. These kind of a qualities they are always hunting as a material part of that, and also interested the materials that have the unique properties, some of the functionality requirement, and some of the unique requirements of the some of the components in the aerospace. They are also searching seriously about that materials have the unique properties. So nowadays the technologies are grown up that now is available, improved electronics and advanced composites and improved paints and sealants and of course is a carbon nanotubes. So nanotechnology areas of interest to aerospace community is mainly they'll see the high strength composites, that is the polymer matrix composite, ceramic matrix composite, and metal matrix composites, and etc. And nano structured material like a nanoparticles, powders, nanotubes, etc. Multifunctional materials and self healing materials. Multifunctional materials means the functionality requirement. Suppose now we are seeing only three-dimensional 3D objects. Now we are making that 4D object. The 4D means that other dimension is becomes the functional requirement. Maybe some kind of a sensors including or some kind of a self-healing material. That means whenever the crack is initiated, immediately it is self-heal that crack. That kind of a materials and sensors, including the sensors, is comes under the multifunctional materials. The sensors may be the physical sensors, maybe chemical sensors, maybe biosensors, and nano electromechanical systems and batteries, fuel cells, power systems, thermal barrier coatings and wear resistant coatings, and avionics, satellite communication and radar technologies, and system integration like nano, micro, and macro, bottom up assembly, that is the impact of manufacturing. Bottom up assembly is nothing but is the 3D printing technology. So nowadays the 3D printing technology is widely using and they are doing a lot of research work in this nano composite areas, different composites and different nano composites, maybe with the polymeric nano composites, how to print and so they are now they are widely testing in that strength point of view and other properties whether it is enhancing or not. So if it is everything is possible, then we can print the component itself. Suppose some component is required in the aerospace, the aircraft, some component. So if you design that component, obviously we can insert into that 3D printing. Directly we can print that the component and you can directly fit that one. So like that, we are now it is a lot of work is going on. The research work is going on in the bottom up assembly also. Apart from that, our conventional materials, they are using that some other nano composite materials and some polymer materials. The engineering materials evaluation, if you see that in the 10,000 BC to the 2020, so the material is the starting with that mostly starting with the metals, and now we are ending with that metals, and we will try to improve that some of the composites, some of the polymers, and some of the ceramics. If you see that metals, polymers, composites, ceramics were used at 5000 BC itself, and now the modern technology slowly it is reduced based on that some of the modernization, some of the limitations in the manufacturing, and some of the limitations on the availability of the materials and their durability. And now again, 1960 onwards, the manufacturing technology or industry 4.0 evolutions is started, and then it is slowly it is booming up again that same materials, ceramics, composites, polymers, and metals. Now, mostly we are looking at most of the composite materials and most of the polymers materials will try to use and will try to reduce the metals and some Some part of the ceramics also we are widely using nowadays. So for different applications. The polymers also we are trying to extract from the natural composites, maybe some kind of a jute, sisal, some kind of a fibers they are extracting, some of the rice husk or whatever it may be, that mostly um, from the natural whatever it is available, those things. So we are try to extracting those polymers, will try to adapt into that the systems. Like that, the growth is making in these areas, polymers and composites. And what is composite materials? Composite materials is basically is required. The one reinforcement is required, and matrix is required, and then finally it will form as a composite. The reinforcement should have that high strength, high stiffness, low density, and the matrix should have the properties are good shear properties and low density properties. And finally, we are expecting some composite material. It should be have the high strength, high stiffness, good shear properties as well as low density. This is called as a composite. So in advanced composite materials that we are mixing, that composite materials is nothing but two or more organic or inorganic components combinations, and it consists of a high strength nanofiber embedded in a matrix. And the materials are the matrix materials are mainly it will useful for that materials that holds everything together. That is the matrix material. Generally, widely we are using the epoxy materials and polyamide, some of the basamide also, and fibers are it serves as a reinforcement. It should be embedded in a matrix. So this is a fiber reinforced matrix composites, and the glass fibers, boron fibers, and carbon fibers. In place of the fibers, you can put the particles, and in place of the fibers, if you replace with the flakes, and different composites are we can classify that. So this is only the laminated fiber reinforced composites. The other particulate reinforced composites and flags reinforced composites, like that we can use the other classifications. Mainly, the mostly in that the aerospace industry, the fiber reinforced composite materials are widely they are using. So that is the reason I have given here as a fiber as a one kind of a reinforcement, and it should be embedded in a matrix. The different fibers are they are using that mostly carbon graphite fibers and boron fibers and glass fibers. So advanced composite materials have that the nanofibers laid out in a tape or fabric form, and put in a mold under heat and pressure, and the resin matrix flows over a nanofibers. Heat is a remover and it is solidifies. It can be formed into various shapes, and in some cases the fibers are wound tightly to increase the strength. Like that, some kind of a preparation methodology I have given here. So this is not a unique, some kind of a preparation methodology. In the based on your preparations, your manufacturing technique, the properties can change, so that the uniqueness of the properties we can identify through that the with respect to the some kind of a manufacturing technology. So in the nanocomposite materials refer to the composites in which one phase should be a nanoscale. That is a morphology such as nanoparticle or nanotubes or lamellar nanostructures type. The improvement of the properties by the addition of particles can be achieved when actually it is a good interaction between the nanoparticle and matrix. Now, earlier the composite is there, matrix, and some reinforcement is there. In the matrix, now we are trying to mixing with that some other nanoparticles or nanotubes or lamellar nanostructures in that as soon as mixing into that matrix, it should have the good interaction between the that respective nanoparticle and matrix. Then only you will get that the good properties. Otherwise, again, if it is not mixing properly, it is not interacting with the matrix material, that whatever the your nano particle or nanotube or other kind of a nanostructure, if it is not interacted with the matrix, then obviously it will not exhibit the good properties at the end. So that the main thing is you have to always look about that, then it should be a good interaction between the nanoparticle or nanotube or nanostructure to the matrix. And uh, and the particles, suppose if you take the nanoparticles, how it is dispersing in the matrix, it should have the good dispersion in the means maybe the equal dispersion. The nanoparticles should be dispersed throughout the matrix in the equally. May not be equally, maybe something randomly it will disperse. Equally we cannot control. So at least should have the good dispersion. That means that some sonification technique and some of the things you have to use, and you can mix thoroughly, and then you can use that matrix for the composite materials. And traditional composites, the length scale of the filler is in the micrometers for the traditional one. The nanoscale is, this is the earth to the football to that the this one is a 10 million times smaller, and then 1 billion times smaller finally for the nanoscale. It is a 10 power minus 9 meter scale. Nanoscale is, so if you compare to your human hair, this is the human hair, and this is the nanofibers. So how the differentiation is like that. It is in the nanoscale. So as soon as some material is comes under that the scale, it is reducing the macro to micro, micro to nano scale. Then obviously the strengths that the properties will exhibit in better and better way as soon as it is reducing the scales. So that is the reason nowadays the researchers try to use that more nano scaled materials into that. So, and why nano composites generally will use? Generally, nano composites is the smaller filler size, and definitely it is the high surface to volume ratio, and small distance between the fillers, and bulk interfacial materials, and mechanical properties. It will increase the ductility without decreasing the strength, and sometimes it will make the scratching resistance also. And optical properties also will improve, that is the light transmission characteristics depend on the particle size. And now if you see that the classifications of the nanocomposites, the nanocomposites is classified based on the dimensional morphology. So this is the called as zero dimension, that is the functional calcite metal oxide nanoparticle composites. It is a one dimensional, like some thin, small, thin layers type one, thin fibers type. This is a one dimensional, and this is a maybe some kind of a flakes type. That is a two dimensional. That is a nano sheets, and the three dimensional. This is some kind of a cubic shapes. Generally, it is called as a three dimensional. So as per the nano composites, the classifications with respect to the dimensional morphology: zero dimensional, one dimensional, two dimensional, and three dimensional. So the further is classified into the nano composites on the polymer based and non-polymer based. The polymer based nanocomposites, so that is nothing but the combination of a polymer matrix and inclusions that have at least one dimension. in the nanometer size range known as polymer nano composite. At least one dimension, that may be the length scale or width scale or thickness scale, where whatever it may be. So that is called as a polymer nano components. So generally it will be that the matrix material will be the polymer. So then we can mix with some of the nanoparticle into that the polymer matrix. Finally, we are going to achieve that polymer nano composite. Other than the polymer matrix, the rest will comes under the non-polymer based nano composites. The polymers are why the polymers are used? Polymers are lightweight and it is of course it is the corrosion resistance material. Polymer matrix for aerospace composites are in the that is polymers have that thermosets polymers, and thermosets polymers is what is the thermosets polymers? It is remains a permanent in solid state. So high stiffness and strength, adhesive properties, as example epoxy, phenolic, polyamide, bismolite, and thermoplastic polymers, that is the remelted back into a liquid, and better impact resistance, high fracture toughness, moderate stiffness, strength. This is polyketone, polyketone, polyether ketone, ketone, like that. So another one is the elastomer polymer. Elastomer polymer is generally it is a viscoelasticity, very weak intermolecular forces, excellent impact resistance, very high elongation, low stiffness strength. Example is polyurethane. Properties depends on the matrix and nanofillers. Improved properties are mechanical properties, tensile strength, stiffness, toughness, thermal expansion, thermal conductivity, ablation resistance, and chemical resistance also. We can use that the polymer matrix nanocomponents. And some kind of a disadvantages are there. Viscosity will increase. That is, we have to seriously study about that viscosity, limits processability, and sedimentation, dispersion, and the distribution difficulties. As soon as if you nanoparticles mix into that polymer matrix, the dispersion, you can't control as such now. So we don't have the special equipment to control the dispersion, because as soon as if you mix that the nanoparticles into that the polymer matrix, it will disperse on the randomly, and sometimes if you are not dispersed properly, then finally it will goes down to the at bottom surface of the container. It will settle down there itself. So that is the reason the mixing should be some proper mixing is required. Some of the techniques we have to use for the mixing properly, and distribution of the particles into that polymer matrix. So it is properly distribute, and you can make it. You can spend a little bit more time and distribute the particles into the polymer matrix properly, and then you can use that um, polymer matrix to making as a composite material. So then, so mainly you have to making some time and the temperature control and viscosity control. So many parameters are there. If you can able to see that all the parameters, then definitely you will get that good uh, nano composite, especially good polymer nano composite. So that is the reason a lot of research work is going on the different types of the processes. So which process is the most efficient? How we can distribute the particles into the proper way, and how to avoid this distribution difficulties, and the sedimentation dispersions, and these all the things now the people are working mostly on that, and they try to some problems they try to avoid, and then it will try to increase that properties. So that is the reason, if you prepare, if I will tell that polymer nano composites I prepared, these the materials. So somebody else is preparing the same thing. So the preparation methodology may be same, maybe hand left method or hand left method, that we can use in that in other in any engineering colleges or any small scale industries we can do it, but with the hand method. So if you do that, the material everything is same, but in person to person the properties will vary. So why it is varying? Because of this, some of the viscosity control and the sedimentation dispersion and the distributions, and maybe the particle size control, the particle distribution control, and how that you are mixing, and what temperature you are making, like that. So now the people are mostly working on this for some manufacturing technique. If you go with this manufacturing technique and using these are the parameters, then you can achieve these properties of the polymer nanocomposites or any nanocomposite materials. That work it is going on. So that suppose if the literature, if you study some of the nano composite material is available, if you try to prepare the same thing at your location, you may not achieve that, you may not get that the same kind of a properties. Properties always it may be the plus or minus. Sometimes it may be you may get the good properties, or sometimes you may get to the lower one also. So that mechanical and other properties also, that controlling technology now, it is lot of research work is going on. So if anybody is can interested can do in that area. So maybe you can identify that some of the unique property, unique process, then you can make it that the unique nano composite material. So like that, if you can able to do, that is the best way. What is the best benefits of the nanotechnology in composite development is, nanotechnology provides new opportunities for radical changes in composite functionality. So major benefit is to reach percolation threshold at low values less than 1% when mixing nanoparticle in a post matrix. Here another one is the volume fractions. Also we have to see that. Volume fraction is nothing but that for total volume. So how much the volume of the nanoparticle you are mixing with respect to the total volume of the total composite. So that ratio it is called as a volume fraction. Sometimes it is the weight fractions also it is going. That is the nanoparticle weight with respect to the total weight of the composite. That fraction also people are working that. Sometimes we can work with that volume fraction. Sometimes we may work with that weight fractions. So we can see that the variations, how much varying from that volume to weight fraction, what is the best volume fractions will give that the best combination and best properties. So you have to see about that the volume fractions, so that whenever you start working in this, start experimenting on this nanocomposite materials, you have to start with that some low volume fractions, that is like a zero point 0.1, 0.2, 0.5, less than, mostly it is the less than 1% volume fractions, and try to make it the composite material, how it is increasing, whether the properties are enhancing or maybe the decreasing, those things you have to see, and then continue our process. So that is the major one we have to think about, that nano composites development, and some functionalities. We can add some of the functionalities. So when the orientation of the nanoscale reinforcement, some of the functionalities can be added. So like this is the some of the nano fibers we are adding into these systems, in that the Z directions, so Z directions. So how we can make it, and suppose some type of a functionality requirement, if you make it, if you add it, and what kind of a nano particles we can add, and how we can extract this functionality requirement from the structure and all. You have to think about that, and you can do some kind of a work and some kind of a research or some kind of a literature you have to do it, and finally we have come into that, okay, these combinations may be sufficient to get this functionality requirement. Then you try to experimentation that you may not achieve that results in the first instant, so you will get that lot of other hiccups to manufacturing such kind of materials. So finally, based on the value interactions and based on the other parameters control, maybe temperature. Sometimes temperature control is also required. Sometimes that proper mixing, so which mixing is most feasible to do that one. That means that nanoparticle mixing into the matrix. These are all the parameters you have to think about that and making the nano composite material. And some of the multifunctionality materials are always we are seeing that the structure plus. The human is intervention is always think about that what is the best one. Now we are making everything is structure. Then now the people are thinking about the structure plus. So that means the most of the cases the major function of the structure is only the carry the load and provide the shape. Then not only this, not only happy with this, then we have to add some other functional requirement also. Maybe some of the sensing one, some of the measurements one, like that. The additional functionality is that some of the actuations, the controlling positions, shape or load, some of the actuations, some of the electrical one either insulate or conduct, and some of the thermal either insulate or conduct. So sometimes the functional requirement is that some thermal resistance, maybe thermal conductivity, wherever it is required. Based on the requirement, the structure can behave like insulated material or conductive material. So like that. So some of the monitorings and control, that is the health monitoring and control, and the structure. So how it is making, if that it is the stress is beyond the limit, then it's obviously going to fracture, going to fail. And that time, how we can monitor and how we can control those excessive loads, or how can heal up among themselves. Some of the stealth technologies is that electromagnetic and visible signatures, and some kind of sensings, physical and chemical variables, and self-healing also, repair localized. Some damages happens, you can repair in localized way. So those things we have to think about that. These are some of the additional functional functions. So I listed some very some few on, and some more functions also we can add up. And building in additional functionalities into load bearing structures. In one key example is sensing function like a strain, pressure, temperature, chemical change, and containment presences. So miniature sensors can be embedded in a distributed fashion to add smartness or functional multifunctionality. This approach is the pre-nano era. So some smart materials like that we are making, and pre-nano era we started this, but now it is continuing with the nano composites, smart materials in the nano. Using the nanotechnology, we can use that smart materials. Nanotechnology, in contrast, is expected to help in assembling materials with such a functional capabilities within the material itself. Okay, so no need to add some two extra components, making that. as a single component. It's not like that. Material itself, if you can put some of the functional capabilities, obviously, whenever you are making that component, obviously it will respond based on your functional requirement. So some of the examples of the multifunctional materials are possible in the principle that design any number of composites with a multiple level of functionality, maybe 3, 4, 5 by using both multifunctional matrices and multifunctional reinforcement additives. So like suppose it's self-healing one, like you can add some capsular into a matrix that contains the nanomaterial sensitive to thermal, mechanical, electrical stress. When this breaks, would indicates the area of damage immediately. Those capsules will blast and it will come and propagate, and those area of the damage it will be rectified immediately. So another capsules contain the healant also, and microcellular structures formed in the matrix may be radar absorbing, conducting, or light emitting. And photovoltaic military uniform also contain the Kevlar for protection generate power during the sunlight for charging the batteries of various devices in the soldier gear. So like this, some kind of a uniforms, maybe Kevlar kind of uniforms. It should be generate some kind of a power, and maybe charging the some of the batteries. There is some of the devices where they are using that soldier in the respective locations. And some of the candidates for multifunctional composites, carbon nanotubes, carbon nanofibers, and polymer clay nanocomposites, polymer cross-linked aerogels, and biomimetic hybrids. And some of the expectations are designer properties, programmable materials, high strength, low weight, low failure rates, and reduced life cycle cost. So these are the expectations, and obviously we'll always will expect the more strength, high strength, and with respect to the weight, low weight, and the failure rate should be very low, and the life cycle cost should be reduced. These are the expectations. And some kind of examples of the self-healing materials are plastic components break because of the mechanical or thermal fatigue. Small cracks, it can become the large cracks, and it is the finally catastrophic failure. And self-healing is a way of repairing these cracks without human interventions. Whenever the small cracks is comes, and obviously it will heal upon themselves. Maybe some kind of a capsules are there. It will that capsules will release the some kind of a material. So that material it will heal into that cracks. Finally, um, it will come back to the original structure. So like that, some self-healing plastics have small capsules that releasing a healing agent when it crack forms. The agent travels to the crack through the capillaries, similar to blood flow to a wound, like that. Polymerization is initiated when the agent comes into contact with the catalyst embedded in the plastic. The chemical reaction forms a polymer to repair the broken edge of the plastic. New bond is complete in an hour at room temperature. Nano reinforcement composites are processing them into various matrices follow earlier composite developments such as polymer compounding, producing the filler polymer, assembly of laminated composites, polymerization of rigid rod polymers, and etc. And purpose is replacing existing material where the properties can be superior, and applications where traditionally composites were not a candidate. Some desirable attributes of the nanoparticles are tremendous increase in surface to volume ratio, increase in solubility, increase in reactivity, possible increase in hardness, that is the titanium nitride. So if you see that nanoparticle integrations, the middle portion is that the nanoparticles, how it is making the polymer, nanopillars, nanocomposites, nanoparticles, and nanocomposite layers assemblies. Finally, nanocomposites vessels coating like that. If you see that polymers and then the nano-filled fibers, maybe the fiber types or maybe the particles types or maybe flakes types, then we can make it some different type of the nano particles, maybe the polymers and how it is interacting, how it is distributing among in that the axis, and how it is exploited the nanocomposites. So suppose this is some kind of a path is there to making that if you increase that path, then obviously you can be making the more resistance like this. So this is the sum of the fiber sizing, and then go to the nano composite layers, and then finally we are coming with the layer technology. So these are the different levels of the processes for the nanoparticle integrations. So we have to control in this the first three steps. To control as much as if you control that nanoparticles or nano fibers or nano structured one here in that matrix, how we can control in the best way. So possibility is there. Then accordingly, what we are going to achieve uh, the nanocomposite that depends mainly in the first process. So I would like to put some of the carbon composite nanotubes, some of the video to play. Check that whether video is audio, whether it will come or not.
And one-dimensional carbon nanotubes in which graphene is wrapped in a cylindrical wire shape.
Because carbon nanotubes have a one-dimensional structure, they exhibit extremely high conductivity in the vertical direction along the wire. On the other hand, graphene that has a two-dimensional structure exhibits high conductivity in the horizontal direction along the layer. So if the two structures are combined, we can expect to get a material that is highly conductive in all directions. Until now, it has been difficult to create this type of structure, but in our research, we discovered almost by chance a structure in which carbon nanotubes are connected to graphene.
Applications that are being considered for this new material are applications that can utilize the characteristics of both nanotubes and graphene, particularly the conduction characteristics.
We at Fujitsu and Semiconductor Leading Edge Technologies have joined forces in an attempt to use carbon nanotubes in LSI wiring. In the future, the nanotube section of the structure that is formed when carbon nanotubes and graphene are joined could be used for vertical wiring, while the graphene section could be used in horizontal wiring. We are also considering the use of this structure to convey heat on a three-dimensional level. Another merit of the composite is the flat surface structure. Normally, when carbon nanotubes are grown on a substrate, there is notable variation in the lengths of the nanotubes, and this variation makes it very difficult to connect with other materials. As a result, an additional process is required to cut the nanotubes to equal lengths. In contrast, this new composite material has an extremely flat surface that makes it very easy to join the composite with other types of materials.
Fujitsu intends to develop synthesis technology tailored to specific applications, and also plans to focus on technology that will enable the structure to be freely controlled. DigInfo News.
Yes. Yeah, they're giving that some of the nano carbon tubes generally. So how it will be the combination to the other materials, and they are showing us some kind of a let's ask about some of the how the nanotubes are forming and how to make it that. So the mainly is emphasizing more on that how uh, that nano tubes or nanoparticles or nanostructured components can be mixed into the matrix, how effectively. That mainly depends on your final achievement of your material requirement. So some of the applications in the nanomaterials, we have the primary structural parts and secondary structural components in the aerospace. The primary structures are maybe the wings, tail surfaces, fuselage sections, rocket motor casting, engine nacelle and cowls, horizontal and vertical stabilizers and pressure bulkheads. And some of the secondary structures like doors, antenna dishes, central wing boxes, landing gear doors, floor beams, tail cones, and flap track panels. These are some of the primary and secondary structural parts that nano materials can be used either in the primary structural part as well as in the secondary structural part also. In aircraft construction, the nanocomposites represent an advanced material solution. In aircraft construction, as a strengthening element for the structure, that is the stringers or frames, or as a skin for the honeycomb type structures used at wings and fuselages. Some of the nanomaterials applications that base materials for high temperature and the carbon composites were developed first for the aerospace technology like components and missiles, re-entry vehicles, space shuttles, and brake lining and brake disc materials for civil and material military aircraft. These materials with non-additive ceramic matrix represents the potential unique solutions for the randoms of the hypersonic aeroplanes. And nanocomposites with the form of zirconia-based complex nanopowders are used as thermal protection for pieces of turbo engines. The fast, better, and cheaper space transportations with nanotubes, how it is evaluated, and what are the different components they are using that nanotubes they have given in the pictorial form. It will be integrated at the aerospace engines and H2 storage and composite aeroshells and digital nano electronics and some of the GPS elements and lithium batteries and fuel cells and micro electrochemical systems, that is the MEMS and NEMS, and electronically operated flight surface smart materials. So applications of the polymer carbon nanotubes industry, different industries and the respective specific applications of the material is the energy industry sector generally use the hydrogen storage devices, energy storage materials, fuel cells, superconducting materials, solar cells. In electronics sectors, molecular computing and data storage, micro electromechanical systems, that is the MEMS, and microelectronics, single electron transistor, ultra sensitive electromechanical sensors, and material and chemistry sectors, that is a polymer, carbon nanotube, nanocomposites, thermal conducting polymer, coatings, ceramics, and metallics, carbon nanotubes composite, tip of a scanning probe, microscopes, that is the membrane and catalyst, and medicine and life sciences is chemical sensor, medical application, cosmetic, medical diagnosis, filter for water, food treatment, and so many other things. Suppose seawater, how to make convert it into that normal water, that reducing the salt, maybe we are removing the salt in that. So also we are using that the nano materials. Some of kind of the filters will use that nano material the filters are using nowadays to purify the water. So these are some of the food treatment also we are using that nano coated or nano composite materials. And maybe nowadays they're using the food packaging also they are using that this kind of a materials. So as soon as if you pack with that food, suppose some temperature should be maintained and maybe 1 hour or 2 hours. Like that, we are using the some of the packing materials also. We are using the nano composites. Some of the specific applications in nanoparticles in aerospace industry is so that is for polishing applications. These are the nanoparticles they are using. Cerium oxide and tin oxide nanocomposites are quicker surface removal, minimum amount of material, improved finishing. The other one is the capacitors, pigments, dopants. These are some of the different applications. These are the different nanoparticles we are using. Uh, Barium titanate, titanium, alumina, iron oxide, zirconium silicate, and titanium dioxide. Wide range of the material based on the applications. These are some of the nanocomposites. So that how we can support pigments, the low cost of material cost, improved physical and optical properties. Dopants is the better uniformity, decrease in the processing temperature, reduction in operating and uh, capital expenditure. So the applications of the nanoparticles is some conductive links, structural ceramics, aluminum oxide, Al2O3 and aluminum titanate, Al2O5Pi, zirconium dioxide. Some mechanical properties enhancing cheap production cost, catalyst, maybe titanium dioxide, selenium oxide, and alumina. It will amplify the activity, better wear resistance, hard coatings, tungsten carbide, alumina, thin coatings. This is using as a thin coatings. Some of the applications depends on the matrix, nanofillers, etc. Maybe in automobile, gasoline tanks, bumper, interior and exterior panels, etc. Electronic and electrical one is printed circuits and electronic components, and food packaging containers, and cosmetic controlled release of the active ingredients, and environment, biodegradable materials, gas barrier, tennis ball, food and beverage packing, military and aerospace applications. So these are the different applications are there. They're using that. Nowadays in cosmetics also they are using that the nanoparticles. They are mixing into the nanoparticles. So some of the ceramic polymer composites and how it will be preparation methodology. I have given that small diagram here. And active ceramic phase and the passive polymer phase. And the properties depends on the connectivity, value percentage of ceramic phase, and spatial distribution of active phase in composites. And some of the advantages are flexible, freedom of design, interest at room temperatures, and some disadvantages also there, less dielectric properties. Applications are now virtual reality games, VR games, and smart garments for the fashion designers. So like that, if you can measure some of the joint angle, if you measure some of the stretch, maybe some of the how much force, maybe in the knee, what is the stress you are making about one item. Some of the sensing things we can use maybe in the foot side, what is the force you are acting at, how much it is, and this controlling, and this is all sensing one. The garment itself is sensing one is there. Some kind of a patch is here. There is some sensors are there. So from the sensors, we can measure it about all the workouts. And the VR, in the VR games, it is so popular nowadays. So like this. So this is the in this they are using the widely in the nano materials. So these are the different applications of the aerospace, the different the sector itself in the different parts of the components. Maybe the hyperspectral imaging and solid state lasers, F-22 inches of aircrafts, modular avionics, and like that, so many other variations and other applications are here and given here as a pictorial form to easily understand that deep space missions. So I want to play another video that is mostly applications.
At very small scales, matter exhibits bizarre behavior. The ability to engineer materials with nanometer precision has allowed researchers to exploit this behavior to produce materials with novel and often exotic structural, electronic, optical, and magnetic properties. Despite propelling far-reaching advancements in the energy and healthcare sectors, however, nanomaterials have yet to really take off in the aerospace industry, partly because of the high risk involved in investing in technologies that have not quite matured to the lofty standard required by this industry. This issue of MRS Bulletin reviews some of the more promising applications of nanomaterials in human space exploration, which contribute throughout a spacecraft's entire journey out of Earth's atmosphere and back. The journey into space necessarily begins with successful liftoff. Even in this preliminary stage, nanomaterials can already serve a useful purpose. Because of their high surface area, nanoparticle fuels are highly reactive and burn at fast rates, making them well-suited propellants for aerospace applications. Researchers must, however, balance this reactivity with careful handling and storage. Coating the particles prevents them from clustering together and losing their highly reactive surface area, but it also reduces the amount of active material in a given fuel, thus decreasing performance. Once in space, whether in orbit or more ambitiously bound for the Moon or Mars, aeronautical systems need reliable ways to produce, store, and transmit energy. Advances in nanoengineering have allowed scientists to develop increasingly efficient and long-lasting silicon-based solar cells. Moreover, research on carbon composites has led to the development of flexible solar cell designs. For example, the Rollout Solar Array, or ROSA system developed in 2014 features a bendable solar cell array capable of unrolling to deliver power supplies and retracting when performing more delicate maneuvers in space. With respect to energy,
Sir, there is a problem. Hello? Uh, Sir, hello? Yes, sir, that's what I was saying. Uh, 5 minutes. I request the participants to kindly wait as the system at Sir's end had crashed suddenly. Just 5 more minutes. I request the participants to kindly wait. Meanwhile, if you have any questions or anything, you people can type in the chat window so that it's easy for Sir.
150 square plus 2 into F1 F2 means 100 into 150 plus cos theta into cos theta is cos 45. How much is cos 45?
5 minutes, please give time. Sir will be joining
Find
us.
out. What about others? Other students? Anybody got a different answer? Anyone got a different answer? Or is it the same? Everybody completed? Roll number 46. Did you complete the solution?
Meanwhile, I would like to know how many of you are able to attend regularly, or you people are watching on YouTube. So if you are watching on YouTube, please make sure that you are making a comment there so that you have watched. We'll have an idea. And also subscribe to the Aero HOD channel.
Okay. Completed?
Sir, I have made you co-host, sir. You can now.
Yes, madam, I am back.
Yeah, I am stopping the screen share.
They may give you resultant work and angles and they may ask you to calculate the two points. Okay, but whatever he gives, the solution is we have to go in the similar manner. Okay, let's look at the section. Okay, now try to do the solution. You are going to. Now I'll ask randomly someone to show your notebook, your solution as well. Question solution. First, be ready. If you fail to show to me, then I'll mark you absent. And don't take much time. Take some 5 minutes, 3-4 minutes is enough. So you know the formula and data is given. Quickly substitute in that data.
So you're sharing the screen, sir?
Yes, yes. Able to see?
No, we are not able to see the screen. That's why.
Now?
Now, yes, sir. Applications, yes.
What is the procedure? Watchman.
So, sound is not audible.
Yes.
Share computer sound.
Expected to yield systems
Yes, sir.
enough energy while reducing
Sir, there is an echo. Sir, you are logged in two devices. There is an echo.
Devices there is an echo. Devices there is an echo. Devices there is an echo. Devices there is an echo. Devices there is an echo.
Hello, sir.
Sir,
Yeah, yeah, I will, 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 yeah, yeah,
Sir, I'm not. There is a lot of disturbance. Please disconnect audio with one device.
hello,
Sir, yes, sir.
now it's okay?
Now it's okay, but screen is not being shown.
Yeah, 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 I will share that.
Yes, sir.
Okay.
Formula is understood when you square it on both sides. Square root.
Can you able to see?
Yes.
Audio is okay?
Yes, audio is not coming, sir.
Okay, audio is okay.
Anybody got an answer? Tell me what is that one? What is that one?
No.
F1 has three user and F2 has one user. Okay, let us take. Let's take the colors. Uh, Roll number 5.
It is there. Stop share.
Sir, audio is not coming, sir.
19. Roll number 12. Roll number
Audio is not coming in. Previously, it came some option. Now I am not getting.
Sir, you have to go to the options and share computer sound. You have to click.
Yeah. Earlier I used to do. Now more options. Disable video receiving.
F1 square plus F2 square equals to 100 you got.
Are you able to see the this video?
F1 F2 equals to you got
No,
this thing.
sir.
Now you have F1 square plus F2 square. You know what is
Yes, some
F1 F2.
problem is there.
How do you solve this one? You can use the a plus b form, a plus b whole square form.
Okay.
And make use of it.
Now I can do
Right.
it.
Okay, we can stop here. Anybody completed the problem? Who is that? Everyone, yeah.
Where is the option? More options I used to receive. Now I am not getting.
Sir, while sharing, you can use the bottom. There will be a tick, sir, share computer sound. That you can switch on.
At very small
Yes, so
and carbon
audio is
nanotube-based
there, sir.
supercapacitors and rechargeable lithium-sulfur batteries is expected to yield systems with dramatically improved energy density while reducing the footprint of the electronics they power. Similarly, memory storage devices based on the mechanical movement of nano-sized switches and levers, and high-performance sensors based on nanomaterials are expected to provide electronics that are immune to radiation and consume low levels of power. Of course, these power systems are only as effective as the astronauts who operate them. Technologies for life support therefore represent another area in which nanomaterials, particularly those based on carbon, can make a significant contribution. Scientists have shown that nanometer-sized holes can be punched into a single sheet of carbon, a material called graphene, to form a super-thin water filter. Additionally, these carbon sheets can be rolled into nanotubes and decorated with nitrogen-based molecules called amines to remove carbon dioxide from the surrounding environment, refreshing the astronaut's air supply. Nanomaterials also show great potential for use in biological and chemical sensing. The combination of various biological sensing elements on a single microchip could allow astronauts to carry a medical diagnostics lab in the palm of their hand. And fully functional electronic noses, or e-noses, built using carbon nanotubes could help monitor levels of toxic chemicals such as carbon monoxide and nitrogen oxides. This need to replenish existing supplies extends beyond life support. There is a similar need to repair, rather than replace, materials while on long space flights. In this vein, researchers have shown that carbon-reinforced parts critical to spaceflight can be repaired by harnessing microwave energy to heat ceramic and polymer-based materials containing multi-walled carbon nanotubes. Scientists envision using this technique to process materials excavated from planetary surfaces. This ability to repair spacecraft materials will be particularly crucial to ensuring protection from harmful radiation in space and from the intense heat generated when re-entering Earth's atmosphere. From liftoff to re-entry, nanomaterials can be utilized in numerous ways to improve the current state of human spaceflight. This issue of MRS Bulletin highlights several of these applications while carefully outlining the technical and financial challenges that remain before they're fully adopted by the global aerospace industry.
Yes, I am back to the normal. Previously, because of my system shut down, and able to disconnect. I'm able to reconnect. I think hardly 10 to 15 minutes time. And please, I'm very sorry. This one. And we'll continue that some of the applications we have shown previously. So there in the video they explained about that the different sectors and the different applications and how the re-entry vehicles and water filter and some other kind of applications they have shown. And now we'll see that specific to the for aerospace industry, what are the different applications we'll see about that. The flame retardant nanocomposites and the nanocomposites with high mechanical stability, stiffness and toughness, nanocomposite solar cells, nanocomposite membrane for gas separation and gas permeability, nanocomposite with gas barrier performance like this. If you see that flame retardant nanocomposites is generally it is the multi-layered boron nitride nano sheets. If you see that here, and single layered boron nitride nano sheets are here. That flame is propagating from one side to the other side. If you can able to make a that path is that long path. If you make a long path, then obviously that resistance will be developed. Suppose the flame will not be propagate from one side to the other side. That is the flame retardant nano composites. Using the nano composites, here the path is increasing. Instead of the direct path, it may be the path will increase and will try to make it some kind of a zigzags one. The zigzags one it will come under itself, material structure itself. So if you can able to change that structure itself, then obviously we can make it that flame retardant nanocomposite. Similarly, for gas barriers also, like one membrane we are keeping as a membrane here. One side is one gas and the other side is other type of the gases. Then this is a gas system energy systems and energy sectors they use that maybe IOCL, NOCL, so many other oil companies and gas companies. They try to developing this kind of a nano composites like a nano composite membranes is this is the gas separators. The gas separators means gas should not pass from this side to the other side. So like it is a clear membrane. Maybe one pipe if you make it if you want to pass in the two different types of the gases, then the how we can make it maybe some proper way like this. And wherever sometimes wherever the gases is mixing properly, if you want to mix some of the gases in the some kind of a portion, some kind of a mixer, some kind of a ratio, then that is also we can control using that nano composite membranes. And this gas barrier, how it is working, I'm making here. This is conventional composites. That is path is mostly it is direct path, some little bit indirect path, but come to the in the nano composites is the tortoise path. That means it is the path is a very long path. It's very long, then it takes long time to come if you then passing from one side to the other side. Like that, that is called as some kind of a resistance. In commercial and industrial applications, advanced composite materials, aerospace paints also they are using, de-icing materials also we are using, and aeroplane parts made by the nano composite. This is the different nano composite materials nowadays they are making. They are showing that these are some materials they are used in 787 Dreamliner. Also now the some of the composites. Now there is 787 Dreamliner is mostly composite, then it is further it is increasing to the nano composites. 50% composites they are using. In that they are now it is modifying to the further into the nano composites. Some of the jet engine applications, engine components, frames, cases, ducts, and fracture toughness. Some of the benefits of the nano composites are fracture toughness, micro cracking, high temperature frame, faces, ducts, thermal conductivity, anti-icing, font frames, electrical conductivity, grounding, bypass ducts, lightning strikes, nacelles, and permeability, composites, hydraulic tubings, and service temperatures, flange compression, high temperature, and frame cases, ducts, coefficient of thermal expansion, CTE, microcracking, the residual stresses, clay buildups, molding compounds, high temperatures, frames, cases, ducts. This is some of the coatings, carbon nanotubes coatings using in the aerospace industry. These are the special coatings. The coatings is in the respect of the some kind of the self-repair mechanisms and maybe some kind of the mechanical, electrical, and thermal properties enhancing nano fillers for piezoelectric paints and micro particulate reinforced one and metal ceramic nanostructure bulk composite materials, nanoclay CFR for barrier of upgrading. The aero coatings requirements is the mainly it is erosion, lightning strike, ice subtension, corrosion. And erosion is dust cleaning, sand, storm, rain, hailstorm, lightning strike. I think you know about that. Heat, shock waves, electricity, electric damage, and interferences. Ice exceptions is mainly rim and glaze. Corrosions is moisture, salt, de-icing, fluids, hydraulic oil, engine oil, cleaning solutions, pressure and temperature cycling, and radiation, solar, moving visible, and IR. And some of the applications, PMNC and CMNC. PMNC means polymer matrix nanocomposites, CMNC is ceramic matrix nanocomposites. I have given here some kind of a flowchart to different nanocomposites for aerospace applications, some of the shielding, some of uh, health monitoring, and tribology, coatings, structures, and here also the CMS. So based on the materials, based on the applications, we are using these kind of the combinations. And these are the combinations right now they have done, and some other combinations also we can work out based on the availability of the material, based on the properties of materials, and we have to test each and everything, whether it is enhancing the material or reducing the material properties or not. We have to see testing and making, and it is thorough testing is required. The manufacturing techniques, the skill, technology is also very much required to achieve that the good nano composite material for any applications, not only aerospace, for any applications. In advanced composites for Boeing, these are the different parts of the components they are using. The Boeing, almost all the components they covered here in the Boeing, that is 757-200 commercial aircrafts. They're already using these are the nanocomposites. So if you see that market trend, the global market is that the trade and is emergence of the zero fuel aircraft will help reduce overall CO2 emission, and growing applications of nano satellites in both military and civil sectors due to their lower mass, and market driver is growing adoption of nanotechnology based coatings on the commercial aircraft will help grow the market. The market is projecting the $5.95 billion by 2021. This is some of the forecast, and some of the attractive opportunities are there. 7.7% opportunities are there. The transportations, mainly mostly they are using the transportation systems. Um, some of the estimated one, this is the 2018 estimated and 2023 projected one, 131.6 billion dollars. So these are the some of the marketing strategies. So that means if you see with respect to this, that uh, mostly the nanocomposite material usage is demand, demanding day by day. So someone can maybe focus more onto this area. Maybe definitely the another 15, 20 years it will be the good opportunities you get it. So much opportunities are other attractive the nano composite market. This is given some of the uh, things. This is all the market sense. I given that the opportunities with respect to the attractive opportunities. So finally, I summarize my presentation. The nanotechnology is enabling technology that will impact the aerospace sector through composites, advances in electronics and sensors, instrumentation, materials, manufacturing processes. The field is interdisciplinary, but everything is start with the material science. So without material, nothing will be there. So material science, everything should be start with the material science. So then the challenges including is novel synthesis techniques. That is mainly the mostly the challenges we are facing right now, and characterization of nanoscale properties. How to characterize, and we have to characterize in proper way and correct way, and large scale production of the materials. So suppose if everything is achieved well, how we can produce the material in large scale as a commercial applications, and some of the application development also. Opportunities and rewards are great, and hence there is a tremendous worldwide interest. This is possibilities for future. Nanotechnology may make it possible to manufacture lighter, stronger, and programmable materials that require less energy to produce than a conventional material. promise better fuel efficiency in land transportation, ships, aircrafts, and space vehicles. The future nanotechnology could very well include the use of the nanorobotics. Now it is a lot of work is going on in nanorobotics. These nanorobotics have the potential to take human tasks as well as the tasks that human could never complete. The rebuilding of the depleted ozone layer could potentially be able to perform. There would be an entire nano surgical field to help cure everything from natural aging to the diabetics to bone spurs, and would have liked to see an analysis for the time estimate to implement the carbon nanotubes in the replacing copper wires. Future of nanocomposites. Polymer nanocomposites are the future for the global packaging industry. And once production and material costs are less, companies will be using this technology to increase their product stability and survivability through the supply chain to deliver higher quality to their customers while saving money. The advantages that nanocomposites offer far outweigh the cost and concerns, and with the time the technology will be further refined and processed more developed. Research continues into other types of the nanofillers, not only carbon and other type of the nanofillers, allowing new composite structures with different improved properties that will further advance nanocomposites used in many diverse packaging applications. So these are the references. Some of the references have given, but some more are there references. I am not given here. So mostly these are the references mostly used to prepare the presentation here. And I'm ending with my presentation with Dr. APJ Abdul Kalam. Look at the sky. We are not alone. The whole universe is friendly to us and conspires only to give the best to those who dream and work. So Abdul Kalam used to say that you have to dream it and you have to work for the dream. I think this kind of a one everything is known. So if you have any questions, I would like to take up the questions.
And all of you can draw this in your notebook. All of you. You can draw this in your notebook. Calculating
Lata
already.
ma'am,
Yes,
I
sir.
completed my presentation. I would like to take up some of the questions from the
Request the part.
audience.
For the first case, I am reading it.
So Himanshu Shekhar is asking some projects to be applied for aerospace industries.
Angle
Okay.
30 degrees are given.
Any suggestion?
Project, projects, it is not specific to the aerospace industries.
125.
Nowadays, the projects
Now, all of
is
you,
specific to
what
the
is
your technology, maybe the some kind of a material. If you want to
now
develop some kind of a material,
619,125 is the
and
given by
that materials,
with all this
what is the functional requirement?
components.
You are making that with respect
Okay.
to material,
Now what do I
and
do? I will make
based
this
on that, then you can choose some of kind of
Now
applications,
what do I do here?
maybe
I draw
relevant to the aerospace applications.
okay.
Suppose in aerospace, we are using a one kind of a component. We have to list out what are the functional requirement of that component, and what is the strength requirements, and what is the other physical and mechanical properties requirement of that material, and what is the existing one, and what we can further improvement. So further improvement, what is the materials already available in that market and existing in that, and if you see that the combination of the different materials, how we can enhance that the properties. Sometimes it may not enhance, it may be decrease that properties also. You have to make sure that how we can make a proper facilities you should have, or nowadays that facilities the everything is commercialized. You will get a lot of the manufacturing facilities anywhere in the major cities. Like Hyderabad, in and around, many things are there. Small scales, small industries are there. So based on their requirement, you have to come up with some of the applications. Based on the applications, you have to choose the materials, and then can come back to that the processing techniques. What are the processing techniques is available? What is the suitable with respect to that? At least you have to test one or two samples, and you can make sure that okay, the properties we are enhancing this may be the maybe the possible, then we can go further to the kind of a work. So, in the projects, if we come back to the projects as academic projects, we can do a lot of things. In academic projects, no need to think too much about that the whether the property is increasing or decreasing, whether it is useful or not useful. So we have to start with that some kind of a methodology, some kind of a proper, some kind of a materials and mixing and proper mixing and how to enhance that the mixing, and we can make a some kind of a process. We can establish some kind of a process, and finally you can give the answer is whether suppose it is increasing the properties with respect to some kind of a value fraction or weight fractions, and you have to experiment it each and everything. Then, so okay, this with respect to this it is increasing. Suppose it is sometimes it may be the decreasing the respective properties of the actual base material. Then you should also mention. So if you use these combinations and these materials, your material properties will not enhance that kind of also. So the research is we can give it always not only due to the always yes or maybe the upgraded one. Sometimes we can mention clearly that these combinations may not work out, and this kind of a process, if you do it, these kind of a problems we may end up with. So better you can choose that some other alternative, or maybe you can choose yourself is that this is the best method you can do for enhancing the that properties and all. I am mainly mentioning about the material properties because whatever you are going to start any kind of a project, so first one is the material is required. So that is one you have to concentrate more on the materials. So that's you have to think about that, and do a lot of literature regarding this, and you have to choose some specific area. You can do some of the literature. What is the existing in literature? What is available? What are the components? What are the materials combinations they are using? What you can do in the better other material combinations to enhance the properties. Like that, you can start some kind of a work, project works.
Thank you, sir. I hope it answered Himanshu sir's question. Dr. Himanshu Shekhar, I think your question is answered. Any other questions from the participants? Okay. So with this, we come to the end of this session, and very nice motivating quote by our beloved Abdul Kalam sir. So universe is friendly to us and to give the best to those who dream and work. So we have eminent professors from NITs and IITs who are joining us for the FPP. And Swamy Naidu sir has taken his time for presenting his knowledge. So I think with the guidance of such all mentors, we can go ahead and also work, dream and work also. So thank you very much for the presentation. On behalf of Aeronautical Department and the team, I thank you for taking your time out.
Yeah, thank you very much, madam. And once again, I would like to give the thanks to the all the your managements, and especially for you and your HOD approaching me. And I would like to congratulate to the participants attending this program. The program maybe it is a 1 week long program. We are going to learn different aspects. To think in better way, you can come back with some kind of a problem statement. Then definitely we are going to help. You require any further help? Please feel free to contact to the mail or maybe the this WhatsApp number. Thank you, one and all. Thank you, one and all, for patiently listening. And of course, in between some hiccups, it happens. That is because of the system shutdown.
So it's okay.
Okay, okay.
Thank you
Thank you,
very
one and
much.
all.
Thank you very much, sir.
Thank you.
It's also resolved by given inclined